Hello, this is Lab 5 by Tyler DiVentima. In this lab, we were mainly focused on observing how a bar magnet fell in different situations, one being through an aluminum foil tube, and the other one being through a regular freefall. Our approach to this was to look at the tube as a collection of rings stacked upon each other to simplify calculations. And in the end, we were able to observe that the bar magnet fell at a slower rate when going through the aluminum foil at 0.76 seconds, compared to 0.27 seconds in regular freefall. We were able to also model this on Python, getting a value of 0.62 seconds for the fall time in our model. To begin making this model, we started with the physical properties that we measured in the physical aspect of this lab. This included the mass of the bar magnet as well as the dimensions of our aluminum foil tube. On the slide, you can actually see the creation of each ring individually of the aluminum foil tube to ease our calculations on line 53. And on line 75, you can see the properties assigned to the bar magnet, including the magnetic dipole moment from our previous lab. On this slide, you can see the functions that we use to do calculations throughout this script. On the top, you can see the function that calculates the magnetic field due to a bar magnet at any position from a previous lab. And on the bottom, you can see a somewhat similar function that calculates the deflux dt due to a magnet on a ring, which will be very useful later on in this script. This loop here shows the actual process of calculating the magnetic field contribution of each ring individually as the bar magnet fell through the aluminum foil tube. What's happening in this loop is at first we record the start time and the end time of the fall through the aluminum foil tube, which will be used to calculate our total time of the bar magnet falling through the tube. And then closer to the bottom, we calculate the current that runs through each of these aluminum foil rings, and then a certain color is assigned to it to show this. To calculate the current running through each ring, we use the deflux dt divided by R method, which is basically just EMF over R, which is the regular equation for current. And this is where our second function shown on the previous slide comes in handy, as you can see. Now, as I mentioned on the slide before, this loop also takes into consideration the B field acting on each ring due to the falling magnet. And this starts at line 173 at the very end of this loop, where you can see we use our first equation to calculate the magnetic field caused by the bar magnet at each of these rings, and subsequently calculate the magnetic force on each of these rings due to the bar magnet. Now, this value isn't exactly what we want because we're trying to look at the forces acting on the bar magnet so that we can better understand why and how it's falling slower through the aluminum foil tube than when that tube is not present. So to do this on line 178, as we iterate through, we just add the value that we get for the magnetic force on the ring to a variable called magF on magnet, because we know these values will be equal due to Newton's third law, I believe, of reaction. And after we have that information, we can see that we can find the total force on the magnet by taking into consideration on 184 the gravitational force and the magnetic force, and summing those together to get the net force acting on the magnet. Now, using Newton's second law, we can use that proportionality to find the acceleration and the velocity and the position of the magnet as we iterate through time. These calculations can be seen on line 189 and 190. As you can see, these lines utilize the relationship between acceleration, velocity, and position as derivatives of each other. Now to the follow-up questions. What if the resistivity of the conductor was reduced as close as possible to zero? How would the dynamics of the falling magnet change? Now, if the resistivity goes as close to zero as possible, this is basically taking the limit of R to zero. And using the equation for current, delta V over resistance, we can see that the current would go towards infinity as this occurs, which would result in a stronger B field opposing the gravitational force of our bar magnet. Now, this would look something like the magnet floating at the top of the tube when it's dropped in, but really it would be falling at an extremely slow rate due to the magnetic field being so strong upward. Now, if holes or slots were cut into the tube, how would this affect the ring currents in our model? Now, if we look at the cross-sectional areas of our aluminum foil tube as rings once again, these holes will make them look more like open circuits, and there will be no induced current that will be able to flow through them. So the magnetic force contribution of these rings upward will end up being zero. So with less force acting against the fall of the magnet, we'll notice that the magnet will fall faster due to the structural change.